Section: Introduction. In this section, we will discuss how we can improve the performance of large language models, LLMs, in complex, multi-step tasks by using self-improvement techniques. These tasks involve interacting with an environment and require the model to complete a sequence of steps. Traditional methods like prompting alone are not enough for LLMs to excel in such tasks due to the lack of suitable training data. Acquiring data for these tasks is time-consuming and expensive, and evaluating the model's performance on each step of a sequence is challenging. Previous studies have shown that LLMs can enhance their performance using self-improvement techniques that rely on zero-shot and few-shot prompting. Instead of using additional supervised training data, these techniques involve self-critique or feedback from interactions with tools or environments. While these methods have shown promise in standard NLP tasks, their effectiveness in long-horizon tasks that demand multi-step interactions in a realistic environment is not well understood. To address this gap, we introduce new techniques to help LLM agents tackle complex tasks more effectively through self-improvement. These techniques involve fine-tuning the model on its own generated data and using unsupervised methods like self-critique to filter training examples. We introduce two new metrics to evaluate the impact of self-improvement, one to analyze the model's acquired capabilities and another to assess the quality of variable-length agent trajectories. Our contributions include proposing strategies for collecting synthetic training examples for multi-step tasks involving environment interaction. We demonstrate that fine-tuning LLMs on synthetic data leads to performance improvements, especially on tasks like the WebArena benchmark. By experimenting with different synthetic data mixtures, we show that all mixtures enhance performance, with the best mixture resulting in a 31% improvement on the WebArena benchmark. Additionally, we introduce auxiliary metrics to better understand the effects of self-improvement on various aspects of model performance and trajectory quality. Overall, our work sheds light on how self-improvement techniques can benefit LLMs in tackling challenging tasks. Section Summary. In this section, we introduce new techniques for enhancing the performance of large language models, LLMs, in complex, multi-step tasks by leveraging self-improvement strategies. These techniques involve fine-tuning LLM agents on their own synthetic data and using unsupervised methods like self-critique to filter training examples effectively. By introducing auxiliary metrics to evaluate capability acquisition and trajectory quality, we demonstrate that self-improvement through synthetic data collection and generation significantly boosts LLM agent performance on tasks like the WebArena benchmark, showcasing improvements of up to 31% over baseline models. Section: In-domain synthetic data. In this section, we collect initial trajectories from the WebArena tasks using the base model. We filter out any trajectories where the model detected failure or where failure was noticeable in the environment, keeping the plausible trajectories. These plausible trajectories are ones where the model may or may not have successfully completed the task. We believe that these high-quality plausible trajectories, filtered to remove low-quality failures, can be used as good examples for fine-tuning without needing ground truth labels. We also explore if the base model can create entirely new tasks, objectives, web pages, and solution trajectories that can be helpful for training. We use the plausible trajectories as a starting point for the base model to generate new tasks and solutions. To ensure diversity and improve generalization, we ask the model to create out-of-domain synthetic examples that are different from existing tasks and objectives, including tasks from websites not in the WebArena benchmark. The WebArena environment is seen as a partially observable Markov decision process with states, actions, observations, and a transition function. The agent model we use is the QWEN 1.5 to 72B chat model, known for its competitiveness and accessibility for fine-tuning. We propose a method to gather in-domain synthetic training examples structured as intent, observation, previous action, leading to the next action. These examples are selected from filtered trajectories collected by the base agent model over all WebArena tasks. For out-of-domain synthetic data generation, we use the in-domain examples as seeds for the base model to create entirely new tasks, objectives, web pages, and solution trajectories. We provide detailed information on the prompts used for generating these out-of-domain examples. We specifically ask the model to generate objectives that are different from previous ones to encourage diverse generations. Section Summary. In this section, we collect plausible trajectories from the WebArena tasks where the model did not self-detect failure or encounter detectable failures in the environment, creating a set of high-quality in-domain synthetic examples for fine-tuning without using ground truth labels. Additionally, we explore generating out-of-domain synthetic data by prompting the model to create completely new tasks and solution trajectories, ensuring diversity and generalization by generating dissimilar examples from existing tasks and objectives. Section: Evaluation. In this section, we evaluate our model using various metrics proposed by the WebArena benchmark. We start by looking at functional correctness, which is a basic metric indicating whether a task is completed correctly or not. This score is either 0 or 1 and is averaged over all 812 tasks in the benchmark. We also introduce a new metric called the capability score. In WebArena, although there are 812 different tasks, many of them actually test the same capabilities but are phrased differently. To address this, we group similar task templates into unique capabilities. A model gets a score of 1 for each capability group if it successfully completes at least one task within that group. The capability score is then the average score across all 136 unique capabilities identified. Furthermore, we introduce another new metric called the vertex score. Unlike functional correctness and the capability score, which focus on task completion, the vertex score evaluates the quality of entire trajectories. It measures the similarity between two trajectories by comparing node distributions within a computational graph. To account for trajectories of different lengths, we propose a modification called vertex_text DTW, which aligns trajectories using dynamic time warping before computing the score. This alignment step ensures a fair comparison even for trajectories of varying lengths. Overall, these metrics provide a comprehensive evaluation of our model's performance in the WebArena benchmark, considering both task completion and trajectory quality. Section Summary. In this section, we evaluate the performance of agents using standard metrics from the WebArena benchmark, such as functional correctness, and introduce new auxiliary metrics to provide a more detailed analysis of agent capabilities. We propose a capability score that assesses an agent's ability to solve unique capabilities rather than just task completion, and introduce the vertex score to evaluate trajectory quality by comparing relational trajectories using embeddings and dynamic time warping to align sequences of different lengths, enabling a more comprehensive assessment of agent performance beyond task completion. Section: Experiments. In this section, we conducted several experiments to enhance agent models using synthetic training data mixtures as discussed earlier. We evaluated the performance of our base agent model M and a simple agent that always stops. This helped us identify which completed tasks should count towards an agent's capability score. We then fine-tuned our base agent model M on 3 synthetic dataset mixtures using a straightforward auto-regressive loss method. This resulted in new agent models M_A, M_B, and M_C. We split our datasets for training and validation, trained with specific settings, and explored iterative self-improvement on one of the mixtures. Our experiments showed that fine-tuning on mixtures A and B improved overall performance, with mixture B showing the most significant improvement. The agent models gained new capabilities through self-improvement, although they might lose some existing ones. Overall, the self-improved agents acquired more capabilities than they lost. We observed that agent models became more robust after self-improvement, especially M_B, which showed improvement in functional correctness. However, M_C was less robust. Additionally, M_A and M M_B maintained most of the base agent model's capabilities after self-improvement, indicating their stability and performance, which is crucial for real-world applications. Section Summary. In this section, we conduct experiments to fine-tune agent models on synthetic training data mixtures and evaluate their self-improvement over the base agent model using various metrics. By fine-tuning on mixtures A and B, we observe an overall improvement in benchmark performance, with the best-performing mixture, mixture B, showing a 31% relative improvement. Additionally, our findings suggest that self-improved agents can acquire new capabilities, although they may also lose some, with mixtures A and B demonstrating the largest net acquisition of capabilities. Section. Is there an effect on the quality of generated trajectories? In this section, we explore the impact of fine-tuning on different mixtures of data sets on the quality of generated trajectories. When we fine-tune on mixtures A and B, we observe no decrease in trajectory quality and even a slight improvement towards the reference on vertex_text DTW. However, fine-tuning on mixture C leads to a decrease in trajectory quality compared to the reference. Training on out-of-domain synthetic examples enables model M_C to exhibit some unique capabilities not seen in other agent models. Yet, upon examining trajectories from M_C, we notice some trade-offs. For instance, compared to M_A, M_C generates longer trajectories, about 1.6 times longer, and more invalid actions, about 3.9 times more. In contrast, M and M_A and M_B do not significantly increase trajectory length, around 1.1 and 1.3 times longer, or the rate of invalid actions, around 1 and 1.3 times more, which helps explain the quality differences highlighted by vertex_text DTW. Since there is no human reference available, the reliability of this evaluation is somewhat limited, as discussed in section. In the appendix, we calculate variations of vertex_text DTW, considering factors like capability weighting and filtering out trivial tasks. However, these variations do not significantly alter the relative ranking of agent models. Our findings align with previous studies, indicating diminishing returns from successive rounds of self-improvement and training on synthetic data. While an agent model may outperform the base model after a second round of self-improvement, it does not surpass models with only one round of self-improvement. Further analysis in the appendix reveals that in the second round, more synthetic training examples can be gathered, but they are of lower quality and contain a higher proportion of failed trajectories. Various techniques have been proposed for self-improving language models, LLMs, including self-distillation and generating synthetic fine-tuning data. These methods can enhance an LLM agent's performance, although they are distinct from self-improvement fine-tuning. Some approaches focus on supervised fine-tuning or handcrafted subprompts to enhance performance on tasks like WebArena. While self-improvement fine-tuning techniques can enhance model performance by reinforcing correct actions, they may also reinforce incorrect actions and biases. Human or supervised filtering could help mitigate this issue, but our current investigation concentrates on unsupervised self-improvement due to the complexity and cost of generating datasets for such tasks. Our analysis of capabilities is constrained by grouping tasks based on intent templates and cosine similarity, and alternative strategies may yield more optimal groups for measuring capabilities. The vertex_text DTW score relies on a strong model, GPT-4, as a reference, but human references would enhance the evaluation's reliability. Future directions could involve evaluating on larger and more diverse benchmarks beyond WebArena tasks.